Hello, welcome to section 3.7, which is about implicit differentiation, or a way we can take the derivative of what we call implicit functions, which is kind of a weird name for it. But an example of this is a regular old circle. So, for example, here's the equation of a circle with radius 5 and center 0, 0. So it just looks like we can draw a graph of it here. So at 5, 0, it crosses the x-axis. Then at 0, 5, it crosses the y-axis. So just that circle. This is the equation of it. So just use that equation to find the y-coordinate when x equals 3, and then solve the equation for y in terms of x. So meaning write the equation so it's in the form y equals something with x in it, and give that a try, and I'll pause it now, and the answers will appear in 3, 2, 1. So for part A, here, I just plugged in x equals 3 into the equation to solve it to see what y would be. So 3 squared is 9, subtracted that from both sides. Y squared is 16. That means y could be 4 or y could be negative 4, and it will get you some, it will work out both ways there. So there are two different y coordinates for this one value of x here. And then if you do part B, this is just a more abstract way of doing the same thing as part A. We're just leaving x as a variable. So I just subtract the x squared from both sides. And here, remember, y could be a positive or a negative number depending on what side of the circle you're on, just like it could have been negative 4 or 4 to make x equal to 3. So when you take the square root of both sides of any equation to account for that, that's why you always include that positive or negative, to account for the fact that y could be positive or negative. So what the section is about is how to take derivatives, how to find derivatives of things like this. But I'm saying things because this isn't really a function, because if you plug in one value of x, there's two different values of y, and that breaks the original definition of what makes a function, which is that a function has only one f of x value for each input x value. And so this is not the graph of a function, so we can't differentiate it. Like, we can't talk about like f of 3 plus h minus f of 3 divided by h, and then take a limit of that as h goes to 0, because what is f of 3? F of 3 could be one of two different things, so this fraction doesn't even make sense. But what we can do is look at it as two different functions. We could say there's a function like f of x that gets you the top half of it. So the top half of it is when the y-coordinate is just the positive square root of 25 minus x squared. That's all of this stuff up here. So if you plug in x equals 3 into this, for example, you'll get positive 4. And then we could write another function for the bottom half. And the formula for the function that gives you the bottom half is the negative square root. And so it's really two different functions. One where if you plug in 3 into this one, you'll get 4. And if you plug in 3 into g of x, you'll get negative 4. And you could take the derivatives of those, and that's what this next example is about. So I'll do this one here. So we're still looking at the same circle, the same equation, x squared plus y squared equals 25. This time, uh, to find a formula for dy over dx, we could do this by writing the circle as two functions, which we already did right here. So this is not the best way to do it, and I'm going to pause it to do it right now. You don't need to pause it because this is not a problem you need to do, but the answer will appear in a moment to A. So here are those results. Just basic a chain rule problem. So you could have done this, but I wanted to just show you that it was kind of a lot of steps. It's doing this derivative twice. It's a little tedious, and you get these two different formulas depending on whether you want the derivative of the top or the bottom. And that works for this problem, but this method isn't going to work for all of these problems because there's all kinds of wacky functions like this that where you can't write y as a function of x, but you might still want to talk about the derivatives of it. So this method doesn't always work. So sometimes we're going to need to do what's called implicit differentiation. So I'll show you what that is now. The basic idea is that you think of this as two different functions. There's the function on the left and the function on the right. And if those functions are always equal to each other, then you should be able to take the derivative of each of them and get the same result. It's just that this function on the left is very weird because y here isn't the same as just the variable x. When you take the derivative of something with y in it, we have to use the chain rule because y itself is a function of x. It changes when x changes. So let's see what I mean by that. So I'm going to take this equation, and I'm going to take the function on the left side, which should always be equal to 25, and just take the derivative of it, like so. And then also take the derivative of the other side. And I'm taking the derivative with respect to x because that's what we're thinking of as the variable here. But I guess you could do it as the derivative over dy too. But anyways, on the right side, this just works out nicely. We just get the derivative of this is just 0 because it's a constant. On the left side, I can take the derivative of the term separately. The derivative of x squared with respect to x, meaning like this is the variable here that is changing. What is the rate of change of x squared as x changes? That is just 2x the regular old way. But this is a more complicated because as x changes, y is also changing in some weird way. It's not like x is equal to y. So the derivative of this isn't just it isn't just 2y. So we're going to have to use the chain rule to say this is actually a composition of functions. The outer function is something squared, and the inner function y is implicitly a function of x. That's what we mean by implicit differentiation. So we're going to write this as plus 2 times the original inner function y to the power 1 times the derivative of that inner function. And that is the chain rule. If you want to, it might be hard to understand why this is a chain rule. Let's just pretend that y was something else other than the y coordinates on the circle. And let's just remind ourselves how this is actually the chain rule. So I'm going to do an example on the side over here. So let's say you want to find the derivative with respect to x of, let's say, I don't know, e to the x squared, then with something like this, you'd say, okay, there's an outer function here, so we're gonna do the derivative of that outer function, which is 2 times the original inner function to the power 1, and that original inner function would still be e to the power x, and then on the outside we would multiply it by the derivative of that with respect to x. And this is just the same thing we did here, it's just that we don't have an explicit formula for it, so we can't really just find this derivative using this. But it's the same idea here, even though it looks weird, it really is just the chain rule. Now that we have this equation here, we can solve it for dy over dx in terms of x and y. So I'm going to subtract the 2x from both sides, so that will make this equation look like 2y dy over dx equals negative 2x. Then I'm going to divide both sides by 2y. So then it will look like dy over dx equals negative 2x over 2y. The 2's will cancel out, and we'll get just negative x over y, which is a nicer formula than what we had before. And actually, these look kind of weird, but they're actually the same, because with this one, well, f prime of x is negative x over the square root of 25 minus x squared, but that square root of 25 minus x squared is actually equal to f of x here. This is equal to the y coordinate on this part of the thing. So I'm going to make that substitution. You could just say this is equal to negative x over y after you replace that square root of 25 minus x squared with the fact that it's equal to y. And same thing with g prime of x here. Well, except in this case, if g of x had that negative sign in front of it, so if I throw a negative sign there, I can throw another one in the top, so I'm not really changing it because they cancel out. And then that would leave you with negative x over y here. So they are actually the same as this. All three of these formulas agree, even though they're written differently. This is just all in terms of x. Okay, so this way seems kind of weird, but we only have to do it once, and also the important thing about this is this works in a lot of situations. There's a lot of things we're going to see also, especially in chapter 4, where implicit differentiation just kind of saves you some time. And sometimes actually it's kind of impossible to use this way on the left. So for example, one of the examples I was going to do for this lecture video was going to be this crazy function over here, sine squared of e to the x equals cosine squared of y equals 0.5. That's just what I came up with when I tried to think of the craziest equation I could. And if you tried to get this crazy equation as like a bunch of different separate equations, like you could have one equation just for this part here and one for the bottom part, but that would only be this one, but then there's a gazillion of these other things, so you're gonna end up with an infinite number of different functions for the different parts of it. So doing it the regular way wouldn't really work. By the way, yeah, it is a pretty crazy graph. Desmos is not giving me enough processing time to actually calculate all of these tiny little things here. It's a large amount of graphing computation that it has to do, so it gave up. and it says it contains fine detail that has not been fully resolved. Okay. Anyways, so things like that you really need implicit differentiation for. So once we have this formula for that, let's use it to find the equation of the tangent line at this point. So first of all, this derivative will tell you the slope. And you notice we're not just plugging x into it, we're plugging y into it as well. Because there's a different derivative depending on which value of y you're talking about. So dy over dx evaluated at that point, 3, -4, is going to be -3 over -4. This negative here was just from the derivative formula. So that cancels out and you get positive 3/4 or 0.75. And let's just look at the graph to see that makes sense. So 3, -4, this is the point that we're talking about here, and the tangent line there looks like it should have positive slope, and we got a positive 3/4. If we plugged in 3 positive 4 into it, this tangent line over here would have had slope, which is -3 over 4. So yeah, you get a different version of the slope depending on which point you're talking about. So now we've got that. We can now find the equation of the tangent line the regular way, using basically point slope form. In this case, the y1 is the y coordinate plus the slope times x minus the x coordinate. And that's the equation of that tangent line. You could simplify it if you want, but we don't have to. Okay, let's prove the power rule. The power rule is the power rule, but if the power is a rational number. So specifically, what we want to prove for this one is so if the power is a rational number, that means p over q, where p and q are integers, and we're going to do this assuming that the power rule works. That the power rule works for integers. Which maybe I should have said as part of the problem. So it's easier to prove that the power rule works for whole numbers, but if it works for whole numbers, this proof here is going to show that it will also work for rational numbers that are fractions of integers also. So let's see how we can do that. So the trick is to write this x to the power p over q as a function where the result is y, and then I can raise both sides to the power q, and doing that makes it so we get y to the power q, and here a power to a power, they multiply, and the q cancel out, so we just get x to the power p. So this equation here is equivalent to the function f of x equals x to the power p over q. Now, both sides of this equation are essentially different functions of x. The right side is the function f of x equals x to the power p. The function on the left side is implicitly a function of x because y itself really is also its own function of x. So we're going to do implicit differentiation here. So we're going to take the derivative of this function on the left side, and for that one, we're going to use a chain rule, which is why I highlighted the inner function in a different color. And on this side, you can just use the regular power rule, which we kind of have to assume works for integers. So this is going to become p times x to the power p minus 1. And then on this side, this is the derivative. The outer function here is just y to a power. So the derivative of that outer function is going to be q times the original inner function to the power q minus 1. And we need to have the original function plugged in, and we also need to use the chain rule here to multiply this by dy over dx as well. And this is what we're trying to find, this derivative. So we're going to then solve this equation. Maybe you can see where this is going. If you want to get a little bit of extra practice, you might want to pause it here and try it on your own, and then unpause it to check your work. But anyways, we're going to solve this equation for dy over dx in terms of everything else. So in order to do that, I'm just going to divide both sides by all of this stuff on the left and on the right. Okay, so that will make it cancel out on the left side, and on the right side, we'll just have this. And then we can simplify this a little bit. First of all, the p over q is just a constant, so we can take that out. Also, the y, remember y is originally defined as p over q. I just made up y to be a placeholder for this p over q function. So that's what we can do here, is just replace it that way. So write this p over q over here. And I'm just going to replace that y with x to that power p over q, because that was the way it was defined. That y was made up to be a placeholder for x to the power p minus q. So there it is. Now we're just going to use the rules of exponents here. So here we have another power to a power. So we're going to multiply this p over q times q minus 1, which that should just become p minus p over q. So we're going to have that p over q in front there, times this other fraction with x to the power p minus 1 in the top, and in the bottom, this is now x to the power p minus p over q. And at this point, if you have x to a power divided by x to a power, we can just subtract the powers. and it gives you just x to one big power, which should be p minus 1 minus the whole power in the bottom, p minus p over q, and the p's cancel out. The minus negative p over q makes it positive p over q, and you can write it like this. And that's what we were trying to show in the first place, was that the derivative of this function is what the chain rule says it should be. What the power rule says it should be, not the chain rule. So yeah, again, this is not really a very good proof because we have to also show that it works for integers, and we haven't really done that here. But we have seen that it works for a few particular integers like 2 and 3. We really did prove that using the definition of the limit back in chapter 2. So here's another example, which is very slightly too wide to fit here. This example is pretty similar to the first example with the circle. It's just a little bit of a more complicated equation with a couple more tricks. So I'll work it out here, but you might want to pause it and try it on your own to see if you get it. Maybe you'll surprise yourself. But let's see. So the first thing I'm going to do is take the derivative of the left side and the derivative of the right side, like so. And in doing that, we need to remember that y is implicitly a function of x, and we're going to have to use the chain rule to get dy over dx whenever we differentiate it. So first there's just the derivative of the x cubed is regular old 3x squared. For this one here, we actually need to use the product rule, which is a little unfortunate. So let's start by just leaving the 2x alone and doing the derivative of the second factor. So there's a 2x factor and then the y factor. So the original 2x times the derivative of y, which I'll write as dy over dx. Yeah, remember it's not just 1, but like if it was x to the power 1, the derivative of just x would be 1. But this isn't x, and we're doing the derivative with respect to x, so this is y, so y is its own function of x, so you have to write it like that. Anyways, then here there's an outer function, which is something squared, so the derivative of something squared is 2 times that something to the power 1, and that should be multiplied by y, and then times dy over dx. And then on the other side of the equation, the derivative of 4 is 0. So this is what we've got. What I'm going to do at this stage is subtract the 3x from both sides so that both of the terms with dy over dx in them are on the same side, like so. And now if both of the terms with dy over dx in them are on the same side of the equation by themselves, we can factor it out, like so. And what will be left on the inside is going to be all this other stuff. There's a 2x plus 2y here, and that still equals negative 3x squared. And now you can just divide both sides by 2x plus 3y plus 2y. And that gives you your formula for dy over dx. It is negative 3x squared over 2x plus 2y. Okay, so that gives you that. Oh, that's not the answer to the question. That was weird. The answer to the question should be the equation of the tangent line. So we can use this to actually find the slope of the tangent line. it's going to be what you get when you plug in 1, 1 into this at the point the question's talking about. So that means we'll get negative 3 times 1 squared divided by 2 times 1. I got cut off there at the end of my recording. I don't remember exactly what I was saying, but whoops. Anyways, we were plugging in x equals 1 and y equals 1 into this, and we get negative 3/4. So that's the slope of the line, and it has the point 1, 1 in it, so still using point slope form. That's going to be y equals 1 plus the slope of 3/4 times x minus 1, and that is the equation of that tangent line. So now we can put a box around it. Okay, so sounds good. And keep in mind that it's a good idea, by the way, if there's a step in this that you don't understand, write a big question mark by it, like, what? And ask about it in class. Ask me in class or ask somebody else how that step was done. It's you don't want to go on being confused about things forever. You could ask a tutor in the tutoring room as well. Anyways, here's practice problems. More implicit differentiation problems. The second one here is a general form of equations of an ellipse, where a and b are constants here. So keep in mind that with constants, the derivative is 0. When taking the derivative of y, the derivative is dy over dx, and when taking the derivative of x with respect to x, it's 1. So these really are 3 different kinds of things. I'm going to pause it now where there's a helicopter overhead and try these problems. The answers will appear in 3, 2, 1. Okay, so here are the answers for these. So for this first one here, the trickiest part, I think, is that you have to use the chain rule twice with this natural log of y squared. One for the natural log, and then again for the fact that you have y squared, and y is itself a function of x. So anyways, the derivative of natural log of x is 1 over x. That's the rule. Here there's an outer function, natural log. The derivative of natural log is 1 over its input, according to the rule from 3.6. And that gets multiplied by the derivative of that y squared, but then y itself is implicitly a function of x here, so we do the derivative of that outer function is 2y, and that gets multiplied by the derivative of that inner function with respect to x. And from here, I subtracted the 1 over x from both sides to bring it to the right side, and then I multiplied by the reciprocal of 2 over y to cancel that out, like so, and this is the formula for dy over dx. This one, part B, is a little trickier than maybe some of the other ones. I think what you might have done here is you might have tried to use the quotient rule to do the derivative of this, which is a thing that you can do. It doesn't hurt anything, but because a squared is a constant, it means 1 over a squared is a constant. So I'm just going to elaborate on that a little bit. If you're not sure why, I can do it like this. This derivative with respect to x of x squared over a is the same as just the derivative of 1 over a squared times x squared. And this is a constant. You can imagine, like, what if it was 1 over 9 squared, 1 over 81? Then you would just be able to ignore it and take the derivative of the 2x. So it's the same thing in this case. As x changes, a does not change. So you can just write it as 1 over a squared on the outside, and then multiply that by the derivative with respect to x of x squared. And that's what becomes the 2x. So this is really just the same thing as 2x and then that times 1 over a squared is where that comes from. And anyways, then we can do the same thing with this other term, but this time you have to also use the chain rule because y is itself implicitly a function of x. So that's how that works out. Let's see. Then, yeah, I kind of skipped a few steps here. I'm subtracting this part from both sides to get the negative 2x over a squared over here. And then you can divide everything by 2 because there's a factor of 2 in both sides of this. So that will cancel out. And then multiply both sides by b squared and divide it by y. It should all cancel out to become this thing. So that is the answer to this. It's a couple kind of tricky problems. Not a very long section, but it's this one tricky idea that throws a lot of people off. But it is a handy technique that we'll use sometimes in Chapter 4. And I'll see you in class on Thursday.